Next, let us talk about color models. First, about the color in the images. Color, as we know just now, is the value that is represented by each pixel in the image. It can be either black and white with grayscale or in true colors. The value of the color in the pixels may need a few bits to be kept. The more bits in each pixel, the color will be more realistic. If it is grayscale, the grayscale changes from one gray to another gray will be more smooth. But of course, the image size will be larger because we need to keep more information. So from here comes the concept of color models. Color modeling is the way we represent colors as number. For our class, we will use the mostly used color model in digital imaging, that is RGB, or stands for red, green, blue model. This model is based on the fact that any color can be produced by mixing the three primary colors, that is red, green, and blue, with different intensities. We take these three components, mix them with different quantity or different intensity, we will get different color. This model is called additive color model because it produces new color by adding the primary color. This concept is used in display. For example, this is an older display. It is CRT. Nowadays, we use more LCD display. But even in CRT display like this, we have arrangement of pixels with color blue, green, and red. And the mixture of this color will give the different color that we want on the CRT screen. And you can see here, this is the mixture of color. Red add with blue, we get magenta. Red add with green, we get yellow. And green add with blue, we get another color that we call cyan. And if we combine them all, red, green, and blue, we get a white in the middle. And since there are three values involved in this color model, red, green, and blue, we can represent them using the three axes of Cartesian coordinate. There will be blue axis, green axis, red axis. So at the origin where all components are 0, we get a black. And at the origin where the component of the red, green, and blue are at the maximum intensity, we get a white. And then the secondary color, magenta, which is the addition of blue and red, we get at this point of this plane, cyan is here and yellow is here. And the other colors will be somewhere in this cube. So RGB was for display devices. For printing devices, there is another color model for it. It is Cmyk, cyan, magenta, yellow, and black. The last K is actually for black. So the letter K in black is put in the model name because B is already used for blue. This model is used because color mixing in ink printing or toner printing is actually absorbing color. Absorb means you subtract the color. Absorbing means the color will be absorbed first and then reflected to our eyes. the effect is subtraction. And this is how we mix them. Yellow add with cyan, we get green. Yellow mixed with magenta, we get red. Magenta add with cyan, we get blue. And if we add them together, we get black. And how this looks like on a printing on paper, for example, you can see this area is a little bit orange because it is yellow added with some magenta here. Cmyk, the black component is actually optional. We can have the Cmyk model without black, or we can have it with black. For example, for this picture, we can represent the picture with only cyan, magenta, and yellow like this. But you see, without black, we have to use so much of color toner, which are expensive. So to save color toner, we can replace some of the color toner with black. For example, this bun in the middle of the picture here, because the bun is a little darker than the surrounding, it has more black component. So if we decompose it into a black component like this, in the cyan component of the bun, you can see here, there is less cyan already. This part becomes white because it is replaced by black. The magenta component also is less because you see over here, this part is white, is less magenta compared to this one. So it is because this magenta is replaced by this black component, and the same thing to the yellow component. You see over here we have so much of yellow toner or yellow ink. Over here we have less. This part almost white. Why? Because that component of cyan, magenta, and yellow are replaced with this cheaper black toner. So this is how we save the cost of printing with toner or ink. So the total cost of this one is less than the total cost of this one, even though this one has extra black toner. But black toner is a lot cheaper, so the total cost is less. Other than these two color models, we also have color models that does not compose color. We have color models that define color according to how human recognize color. For example, human consider color to have intensity or lightness, hue meaning which color it is, and also how saturated, how pure the color is. Saturation means the purity of the color. To use this color feature, there are two more color model that employ this concept. First is HSV, hue saturation value, this one, the first picture, and the other one is HSL, hue saturation and lightness, the second picture. You see, it is not Cartesian coordinate anymore, it is cylindrical coordinate because hue requires degree to be its unit, so we need a kind of polar coordinate, which in this case is cylindrical coordinate. So in HSL, lightness goes up, it becomes all white, bottom is all black, and for HSV, the same axis is value, which is less in darkness, and saturation is the value from the center to the point in the cylinder.